Calculate the intensity of sound waves from an electric guitar's amplifier at a distance of 5 meters when its power output is equal to each of the following values. So we can regulate the power of the sound emitted by the guitar's amplifier if it's set on 0.25 watt, applying the formula as long as the waves are considered to be spherical waves. So I is equal P over 4 pi r squared. 0.25 watt is given, and 4 pi is squared. Do not forget to square the distance below. Meter squared, so it's 7.9 times 10 power minus 4 watt per meter squared. Similarly for parts B and C. So if you notice that as the power increases, what happens to the intensity? The intensity increases too. So the power, and for the same distance, the power and the intensity of the sound are directly proportional. And here I would like to note that a number times 10 power minus 3 is greater than a number times 10 power minus 4, because if the power is negative, as we go higher in values, the magnitude of the whole value is actually decreases. So we say that the order here is greater than the order in part A. Now, part 2, at a maximum level of loudness, the power output of a 75-piece orchestra radiated as sound is 70 watt. What is the intensity of these sound waves to a listener who is sitting 25 meters from the orchestra? Same thing, I equal P over 4 pi r squared, 70 watt over 4 pi, 25 squared meter squared. The result is 8.91 times 10 power minus 3 watt per meter squared. Now, if the intensity of a person's voice is, now we are given the intensity 4.6 times 10 power minus 7. See how smaller is the intensity of a person's voice than the intensity of the orchestra, because the order here is 10 power minus 7. However, the order for the orchestra was 10 power minus 3. So this is a big difference. Now, I equal P over 4 pi r squared. To cross multiplication here, I could be considered to be I over 1. So P times 1 equal 4 pi r squared times I. Do the substitution. Don't forget to square the r. And you get the power in the watt. 2.3 times 10 power minus 5 watt. Now, how much power is radiated as sound from a band whose intensity is 1.6 times 10 power minus 3 watt per meter squared at a distance of 15 meters? Again, given the intensity, given the distance, we are supposed to calculate the power. Do cross multiplication. 4 pi r squared I, so it's 4.52 watt. The power output of a tuba is 0.35 watt. At what distance is the sound intensity of the tuba? 1.2 times 10 power minus 3 watt per meter squared. So here we are given the intensity, we are given the power, we want to find the distance. So we have r squared is P over 4 pi I, because if you do the cross multiplications and work it out, you're gonna get r squared is P over 4 pi I. Do the substitutions, you get r squared is 23.2 meters squared, but we're looking for r distance, so we have to do square root for the value, for the obtained value, for both the value and the unit. So radical 23.2 meters squared is 4.8 meter. Now, problem solving. Problem 1, the variation, studying the variation of intensity as a function of power. I've just mentioned the result or the conclusion in the previous parts, but let's do another activity here to confirm the idea. So source of sound S and a receiver R are separated by a distance R. In the first case, the energy carried by the emitted sound wave is E, and thus its power is P. So the source here is said to carry energy E, or to have a power P. And in the second case, the energy carried by the emitted sound wave is E prime, and its power is P prime, such that P prime is double P. So the next time, or in the second case, it is giving the double, or it's carrying double the energy. It is flowing at double the rate, having double the power. So the question here is to find a relation between the intensities I and I prime of the wave with respect to the receiver R in the first and second case respectively, and then draw out a conclusion about the variation of I as a function of P. So what do we have here? Solution. Let's start. I want to find the relation between I and I prime. So I'm going to start with I prime to see how did it vary with respect to I. What happened now? Well, now what's the result of I prime? So I prime is P prime over 4 pi R prime squared. We're given that P prime is equal to 2P and that we're studying in both cases the intensity of the sound having the source and the receiver set at the same distance. So R prime is equal to R. We did not change the distance between the source and the receiver. So R prime could be written as R2. So we have 2P over 4 pi R squared. Factorize, take 2 as a factor. So 2 times 10 times P over 4 pi R squared. This is actually I. So it's 2 times I. That's why upon doubling the power, I prime was also doubled. So it's equal to 2I. So as a conclusion, for the same distance r, as the power of the sound wave increases, its intensity increases. And I noted this in the first exercise here. I said that as the power was increasing, we can notice that the intensity was increasing too. Now problem 2, variation of intensity as a function of distance. Now source of sound S and power P. So now we are going to keep the same power, but we are going to move the receiver further away from the source such that R prime is double R. Again, the question is find the relation between the intensities I and I prime of the wave with respect to the receiver R in the first and second case. Then draw out a conclusion about the variation of the intensity as a function of R. So what happens to the intensity when R is varied, when R is increased, for example. So starting in the same way, starting from I prime is P prime over 4 pi R prime squared. We have P prime is equal to P. So we did not change the power here. And 4 pi R prime is double R, all squared. So you have to distribute the square now for 2 and R. So it's 4 pi 4R squared. Factorize, take 1 over 4 as a factor. We are left with P over 4 pi R squared. Why do we have to factorize? Because I want to obtain one of the factors here to be equal to I, so that I find a relation between I prime and I. So 1 over 4, this is actually I. So I can see here that upon increasing the distance, I prime is quarter I, so it decreased, it did not increase. So for the same power, as the distance r between the emitter and the receiver of sound increases, its intensity decreases with respect to the receiver. Problem 3, intensity of a sound wave. The intensity of the sound from an explosion is 0.1 watts per meter squared at a distance of 1 times 10 power 3 meter. Find the intensity of the sound at distances of 5 times 10 power 2 meters, 1 times 10 power 2 meter, and 10 meter. So you have to keep in mind that as long as you are not given that the power is changing for a certain source. So this source have a certain power, okay? So it's characterized by the power of the sound it emits. So we have here the source, we have different distances, and thus we will obtain different intensities, I1, I2, I3 at different distances. So the point here is that, for example, you are given the intensity at this position, and you are asked to find the intensities of the same source at positions 1, 2, 3. So you're supposed to find I1, I2, I3. So in the first step, in order to find I, and you're given the distance, you need the power. So let's find the power from the first case, in which we are given the distance and the intensity. Then use this power to find the intensities at the other positions. Yani I equal P over 4 pi R squared, P equal I 4 pi R squared. Do the substitution for the first case here, for the first given here, and you will obtain 1,256,637.061 watt. Okay, now we can use this power for I1, I2, and I3. So I1 P over 4 pi R squared at the first distance, which is 5 times 10 power 2. Don't forget to square it. And then I2 at the other distance, 1 times 10 power 2 all squared, and then I3 at 10 meter squared. And we're going to obtain different values for the intensity. So if you notice here, as which one is the greatest distance here away? So we have 5 times 10 power 2. So here we notice that as the distance decreases, the intensity increases.